That's it. Good morning, everyone. I guess good morning to those who are joining us in the Rocky Mountains, and good afternoon to the East Coasters out there. Today I'm going to be talking about a new series of hackathons that we're working on at Fluid Numerics with OS Hackathon, where we're focusing on helping teams leverage AMD's ROCm platform, and specifically HIP and some of the HIP accelerated libraries. If at any time during the presentation, if you have questions, feel free to reach out on the chat, and we'll do our best to respond to those as we go. So last week we kicked off the HIP Hackathon series with a virtual event. We had one team join, Ronald Fernandez from AIMonk Labs over in India. He got to work with myself at Fluid Numerics and Alessandro Fanfarillo over at AMD. During this week, well, I guess during last week, for this event, we looked at the Darknet application. This is a object detection and labeling code written entirely in C++ and CUDA. Some of the there's options to build this code with cuDNN in the back end for more optimized performance on the Nvidia hardware. And basically, our goal for the week was to convert this code, both the CUDA kernels, the cuDNN layer, and some of the accelerated libraries over to the AMD ROCm ecosystem so that Darknet can be run on both AMD and Nvidia hardware. What this really entailed for us was basically taking all the CUDA kernels and transitioning them over to HIP, and then we had on the plan to basically transition cuDNN over to MIOpen. So cuDNN in the Nvidia software stack is something that's really only it's hand-tuned kernels with an API in front of it to run optimally on Nvidia hardware. MIOpen is the equivalent on the AMD ROCm side. All right, so let's talk a little bit about the strategy. So before the event, we got together and tried to figure out, okay, how we're gonna do this transition process. But essentially, what we wanted to do was start with the upstream from a repository that's owned by Alexi AB on GitHub. We'll fork from that, and we make sure that we can run a verification example on the existing hardware where that code's supposed to be able to run, which is the Nvidia hardware. From there, we go through a process to HIPify the code, and I'll talk a little bit about the strategies here we took there in a couple slides. Once we're able to HIPify, then we want to rerun those same exact verification tests we started with on both the AMD and Nvidia hardware before we start claiming success. In terms of the daily process, so this hackathon, we did a 5-day event for this hackathon. Every day, Ronald, myself, Alessandro got together, did a half-hour daily stand-up over Google Meet, talked about some of our strategies, some of the hurdles we're facing, and kind of course correct throughout the week to make sure that we're kind of following this 3-point strategy. Of course, having Alessandro's help from the AMD side greatly helped us knock through a lot of the issues we came up with while doing this porting process. So these calls really help kind of accelerate that time to solution here for us. The other half of it, for the rest of the communications, you got to remember. Alessandro and myself being in Boulder and Ronald being over in India, we're 11.5 hours apart. So we did our best to keep in touch throughout the coding time over a Discord server so that, again, as things are going on, we can just rapidly knock through some of these issues. So let's talk about what we actually were, before I get to that, for the compute platforms for this event, we needed an Nvidia system where we could start a lot of the work from, do the HIPification process, and make sure that we can at least build the code for AMD hardware. And of course, once we had the HIPified code, we needed to make sure that we needed a platform where we could run that code and make sure we're running, getting the correct answers on AMD hardware. So on the Nvidia side, we used the OS Hackathon's OS HPC cluster. This is a cloud-native HPC cluster with a Slurm job schedule that's hosted on Google Cloud Platform. In terms of the software that's available, we're running on a CentOS 7 operating system. For CUDA, we're using the CUDA 11.1 toolkit and ROCm 4.0.1. On the AMD Accelerator Cloud, AMD provided some time for us on their compute systems to give us access to the MI50 and the MI100 GPUs for testing. And in terms of the software stack there, we were looking at ROCm 4.1.0 and the Ubuntu 2004 operating system. So let's I'm going to walk you through some of the highlights during the week we had, and we'll kind of go through these steps one by one here. So the first part here was basically where we started, fork and verify. We decided to primarily look at the inference side of running Darknet. So basically on the inference side, what we're looking at doing is sending in images and having Darknet tell us, what's in it. And in this example here, it's a picture. It's got a dog, a bike. There's a truck in the background. We had, I think it was like a suite of 6 of these images. Essentially, we'd run through and make sure that those detections are happening, and they're also getting the correct labeling in place. So this was our test case. If you're interested, if you're a Darknet user, we use the YOLO v3 weights and some of the YOLO v3 configuration files to drive that neural network evaluation. Now, on the first day, we did uncover some upstream bugs in Alexi AB. So as I mentioned before, Darknet can be built with cuDNN, or it can be built with the handwritten CUDA kernels to do the neural network evaluation. We found that the cuDNN version did get us the correct labeling, but when we just ran with just the CUDA kernels themselves, the inference was happening, but the actual labeling of the images weren't occurring. Good news there, Renault was able to open up an issue with Alexi AB and resolve that problem. And as of a couple days ago, this issue has been closed in the upstream, and of course we've got that into our fork. So now we're basically at a stage where we know we can run on the NVIDIA hardware, we know the answer we're supposed to be getting, and basically from here we know we have something that we can really start doing the HIPification process on. All right, so in terms of the HIPification steps here, what we have going on is we decided on 2 strategies. So basically on Tuesday and Wednesday, we spent most of our time trying to suss out what's going to be the cleanest way to do this. Now, some of the requirements Renault has, we wanted to be able to get this code back into Alexi AB upstream. And usually when you're working with a large community code with about 15,000 users, you got to be careful about how many changes you push back and basically have the original maintainers of the code try to take on. So we wanted to keep the amount of changes as minimal as possible. So the first approach here was to just add a pre-build make script that can be run before calling make install with the Darknet make system. And what this script does is essentially goes through and it runs the HIPify Perl script that comes with ROCm to convert the CUDA code, the C code, and any of the header files over to HIP. Essentially, this does a search and replace for any of the CUDA API and swaps it out with the HIP or ROCm API calls. We found some other minor issues in there you might see in the code. There's some issues with the chevron syntax. There's a couple files where the NVCC compiler from NVIDIA is a bit more permissive with some of these syntax issues, and we found some instances where there were spaces between some of the chevrons and the CUDA kernel launches. So you could see in that first for loop where we're looping over those .cu files, we're basically doing stream editing to kind of clean those up. So again, while NVCC, it might be okay with that, HIPCC is a bit more strict in some of those issues there. Outside of those cleanups, there was a couple spots where we had to add in some C pre-processing flags. The ROCm ecosystem, and particularly the HIP API, does not have functionality yet for working with the CUDA graph API. So basically, wherever we saw these CUDA graph calls, we're kind of riding by the seat of our pants here, but we put some C pre-processing flags around that. Basically, if we were building for AMD hardware, we just had HIPCC ignore those statements, and thankfully that turned out not to be an issue for correctness for the verification. Now, the other strategy we tried, it's a little bit more invasive, but in some sense it has some nice qualities to it. And we'll get to that in a minute here. But essentially what we did is we consolidated all the include statements and all the definitions for the CUDA API and the HIP API into one header file called gpu.hpp. Now, when you run with HIPCC, there are C pre-processing flags that are defined. If you're building for an AMD hardware, the pre-processing flag that seems to be stable is HIP ROC CLR. You can see it on the top there. And then if you're building for NVIDIA systems, you usually have HIP platform NVCC as a C preprocessing flag. So it allows you to selectively compile different sections of code. Now in the top section, where we're basically looking at the positive for if def HIP ROClr, we do the includes for all the HIP runtimes, and in this case, Darknet depends on the cuRand or HIPRAND here, and the HIP-BLAS API. And now if you're building for NVIDIA systems, of course we consolidate all the includes for the CUDA API into this header file down below. Now the other thing you have to do in the header file, if you're going with this kind of approach, is to basically remap through defines macros to take all the CUDA API calls and map them to the appropriate HIP API calls. There's tons of documentation online, so essentially we sat through, I believe it was about 140 distinct API calls that are made in Darknet and enumerators that are available. We just basically had to map all those out in there. Now if you did want to see this complete file, just to get an idea of how this works, you can check out the OS Hackathon fork on GitHub of Darknet, and this is in the source code there. So in terms of how invasive this was, so we added a new file, this gpu.hpp header, and then of course we also had to migrate all the include statements for CUDA out of the original source code and into this GPU header. So there's a bit more modifications involved, but the upshot here is that as a maintainer of the code, this is readily available for debugging purposes. So you know, if you go think about the other situation where basically what you're doing with the pre-build script is you have committed in your repository the original CUDA code, but what you actually end up compiling to make your executable is something that goes through another process. It gets basically, right, it gets HIPified, and then we do some string editing on it. So in terms of maintenance and debugging, we decided to stick with this particular strategy simply because the original authors would be able to see very clearly what modifications were made, and they wouldn't have to worry about things changing before basically going from source code to a binary file. And for both strategies, you know, this strategy worked. Basically, we went with the header strategy for this particular code, but in either strategy, we did have to do a couple modifications to the make system. So one, we added to the Darknet's make file system, not the CMake system, two build variables. One is use ROCm that can be used to toggle on and on whether or not someone wants to use HIPCC to compile, because the nice thing is with both approaches, you can still just use the original NVCC GNU compiler builds. But if you switch on use ROCm equals 1, essentially the make system will look for HIPCC and go through the compilation process that we set up here underneath that particular conditional path. For the HIP platform, basically what we need to be setting here is we need to tell HIPCC whether or not you're building for an NVIDIA system or an AMD GPU. And this is where we ran into some nuances with some of the version releases from ROCm, particularly version 4.0.1 HIP platform. You set either to HCC for AMD hardware or NVCC for NVIDIA hardware. When you switch over to ROCm 4.1, you use the keyword AMD for AMD hardware and NVIDIA for NVIDIA hardware. Just some minor nuances there. And again, you know, there were some other modifications that are you can check out in the Darknet make file that's on the OS Hackathon fork, and includes you know, additional compiler flags, linker flags that need to be put in place in order to link in the HIP-BLAS, ROCblas, and HIPRAND. Now in terms of the Arch, so Darknet in their makefile system has a variable called Arch that was originally used just for specifying the target architecture for the NVIDIA GPUs. So this would have been, you know, like the SM72 for the V100s, or SM80 for an A100 GPU, etc. We expanded the ability of that section where the Arch is specified to accept variables for the AMD MI50 and MI100 GPUs. So here, you know, for our test cases, we were looking at the GFX 906 for the MI50s and then the 908 for MI100s. Now, all this is said, and I'm giving you a lot of highlights here. Basically, it took us until about Thursday to get to this point where we had not only the verified code in place, we did the HIPification process with both strategies. It wasn't until late Thursday afternoon that we got confirmation that, one, we can run on NVIDIA GPUs with the HIPified code, and then on Friday afternoon, we got the confirmation that this could all actually run on the AMD GPUs. Well, Friday afternoon for us, so early Saturday morning for Renault. This was definitely a huge success that we could actually get the same results with the CUDA kernels, with the upstream fix that we pushed back to Alexi AB, and now we've enhanced the portability. So at the last slide here, I just want to share with you just one more proof that we're running on multiple GPUs with the same bit of code after 5 days of work across the globe virtually through this hackathon. I'm showing you here some of the run times of the inference for the YOLO v3 weights with Darknet for a few different test cases, including that dog, bicycle, and truck picture we have there. So on the y-axis, you're seeing run times in milliseconds, and then going left to right, we're transitioning between each of the different verification tests there. So on the upshot, what this says to me is, basically we went from having a code that can only run on NVIDIA GPUs. We can now run on both platforms with the same piece of code. We hope to actually now get this merged in to the upstream so that other Darknet users can benefit from this. The last steps we're still working on here, we're cleaning up some of the migration process from cuDNN to MIOpen and getting that tested. We have some make system and documentation cleanup just so everyone knows how to take advantage of this new platform, this new portability that we've introduced into the code thanks to ROCm. And we're going to get a pull request into Alexi AB to get all these new great features into Darknet. Now I did just give a whole bunch of highlights here from the week. If you want to see a lot more of the details, including some of the bugs we ran into during the week, with a bit more details on how we got a lot of those resolved, you can check out the oshackathon.org site. Just go to events/2021 Spring HIP Hackathon. If you want to learn more about OS Hackathon, of course, you can go to the OS Hackathon website. You can find us on Reddit, Twitter, Facebook, and of course on GitHub. A lot of the repositories that we work on for this event, including the infrastructure as code for the OS HPC cluster, can be found up there on GitHub. So if you want to see how we operate an HPC cluster for these events, we're happy to share that with you guys as well. If you want to learn more about Fluid Numerics and our involvement in these events, of course, you can check out our site. We're also on Reddit, Twitter, and LinkedIn. And you can also find a lot of the stuff we do on GitHub. Now's the time for the Q&A. If you guys have any questions about hackathons in general, about this particular event, about Darknet, I'd be happy to field any questions you might have for us. I'll hang out here for a few minutes. But feel free to use the chat window here on YouTube to ask me any questions. Okay, let me refresh here. Okay, so I got a question here from Angelo. Thanks for sharing. Could you comment on why the performance of HIP converted code running on AMD MI50 and MI100 cards was significantly poorer when compared to the NVIDIA cards for which the code was originally wrote? Yeah, so that's a really good question. So really our focus for the week was really to make sure we can get correctness on a variety of hardware. I did notice in the code there's one spot where the block size is hard set for all the CUDA kernels that exist in Darknet. Typically this is not the best thing to do. Usually each kernel has its own optimal setting in terms of the grid and block size, the amount of shared memory you allocate for each, and so there's still a lot of work that needs to be done to tune the code for each specific architecture. I suspect since Darknet's been running much longer on the NVIDIA hardware, the developer teams had a lot of time to really get that performance dialed in with that limited set of settings. I would say that a good next step for this project, though, would be to start looking at profiling the individual kernels and doing some tuning there to get things running, I guess, more performant on those AMD systems. And I'm sure the same could be even said for the NVIDIA hardware. So I hope that answered your questions. If you do have a follow-up, feel free to post that as well. Yeah, any other questions you guys might have about performance? Since this is a community code, basically, Renault came in because he's a user of Darknet, and I'd encourage anyone, I guess, if you're interested in carrying on this work, we'd love to continue working on these community-driven codes. These are all areas I think that do need support across the board, and this is constantly a thing that we chase, making sure that the target hardware folks want to run on it is the code is optimally built for that.
He says that did answer his question.
Awesome. So we'll give it a couple more minutes here. But if you do end up wanting to reach out to us, I'll go ahead. I'll update the description in this video with a way for you guys to get a hold of us and talk to us more about hackathons, about this code. Just want to make sure you guys. We want to get you involved in the community in some way, and any way we can to get you on board to help out with these codes, help you out with your codes, we're happy to do it.